Hello and welcome to the Too Long Didn't Read version of my linear motion lecture. While I tried to be as simplistic as possible in my previous lecture, I still realized that it was very complicated math and could have been opaque considering that there is no algebra prerequisite for this class. With that in mind, I'm going to go through a simplified version of the lecture, which doesn't necessarily go through every example and doesn't necessarily justify all of the math that I use, but does hopefully give an intuitive understanding of what is happening and does give the most important equations that you're going to be using throughout this course. Because linear motion is the study of motion, and so are Newton's laws of motion, you need to be able to understand this in order to go forward with the course. With that in mind, I am going to begin. For our first definitions, we're going to talk about position and distance traveled. Position is a vector quantity which tells where something is, usually given by the variable x for one dimension or r for multiple dimensions. Distance traveled, d, tells us the absolute amount of distance traveled over the course of an action. So position is a vector quantity and distance traveled is a scalar quantity. And one of the main differences that you're going to find is that if you run around a track multiple times and end up in the same position where you initially started, your position is going to be the same, but the distance traveled is going to be some value because you've been running around the track, even though you ended up in the same position where you started, you have traveled a distance. Both are measured with units of length, which are meters, which is about 3.2 feet, or kilometers, or miles, or etc. The average speed is given as the distance traveled over time. It has units of length per time, or meters per second, kilometers per hour, miles per hour, etc. This is the average speed. You could be going faster on the freeway and slower on the parking lot, but this will only give you the overall average speed that you were traveling. This can be written as V average equals delta D over delta T, where delta means that there is a change in something. So delta D over delta T is the change in distance over the change in time. Instantaneous speed you are going is the speed you are going at any given moment, and is the speed that you'll read on the speedometer, and is written as V instantaneous equals dd over dt instead of delta D over delta T. This is because of the definition of what instantaneous means. Instead of averaging out a distance that you're traveling over a long time period, you take the time period and try to go as small as possible to approach zero and see how much distance you've traveled in that approaching zero time period. So this is called the derivative, and practically you can only approach measuring the instantaneous speed and not actually measure it. So velocity is the vector version of speed containing both magnitude and direction. The magnitude of velocity is the speed at which an object is moving, where v velocity is equal to dx over dt, where v and x are both vectors. So what is the distance that you travel with a constant speed? If v average equals d over t, then doing some algebra, multiplying by t on both sides will give us d equals v average times t, which makes sense because if you're traveling at 80 kilometers per hour for 1 hour, then you are going to be traveling 80 kilometers per hour times 1 hour equals 80 kilometers. If you are traveling 80 kilometers per hour for 3 hours, that means every hour you traveled 80 kilometers and you traveled for 3 hours. Therefore, the distance traveled is going to be 80 kilometers per hour times the number of hours that you traveled, which is 3 hours, which is going to be equal to 240 kilometers if I am not mistaken. And then this also generalizes to the vector form for x and velocity instead of d and speed. Our final quantity that we're going to define is acceleration. If velocity is the rate of change of position over time, acceleration is the rate of change of velocity over time. So units of acceleration are length per time, which is the units of velocity, divided by time, which is equal to length per time squared. The units of acceleration in SI units are meters per second squared. They can also be given as kilometers per hour squared or miles per hour or several other types of units. Acceleration is the change in velocity over the time interval and is therefore given by this equation, A equals dv over dt. If we know this, how do we do calculations based on this? Now, I am not going to justify this as well as I did in the other lecture, but basically, the kinematics equation for constant acceleration are given by position equals the initial position, which is what that underscore 0 means, plus the initial velocity times t, plus 1/2 at squared, where a is the acceleration. And the velocity is given by the initial velocity plus at. So I am leaving these in vector forms to be more generalizable in the future, but for the moment, all we have to worry about is whether or not x is positive or negative, or v is positive or negative, or a is positive or negative, because that is basically what it means to be a vector in one dimension. As a final check to make sure that this makes sense, let's check the units. The units of x are length, and then on the other side of the equation, we have x, also units of length, plus units of velocity times time, plus units of acceleration times time squared, which is going to be equal to length plus length per time times time plus length per time squared times time squared, which is equal to length. All of these are going to be units of length, which checks out on the left-hand side of our equation. We're looking for position, and on the right-hand side of our equation, all of the units that we're adding up are equal to length. For velocity, you have length. The units of velocity are equal to the units of velocity plus the units of acceleration times the units of time, which is going to be equal to length per time equals length per time plus length per time squared times time, which is going to be equal to length per time all across the board. While we did not justify our use of this equation, we know that it has to look something like this because we have these units of acceleration, which are length per time squared. So it has to be multiplied by time squared in order to get your units of distance. Now let's do something that isn't in the book and look at some position versus time graphs. For a stationary object, x is just staying at the same point, which means that there is no velocity because x doesn't change position. Therefore, velocity is 0, and because velocity is constantly 0 and doesn't change, acceleration is also 0. For uniform motion, we have a constant velocity, which means that acceleration is still 0 because velocity doesn't change. But the position versus time graph is going to be a linear function, which means that it's a straight line going up. Because velocity is constant, that means that every time period you are going up and changing your position the same amount of position over a given time. That is the definition of a linear function. For motion with constant acceleration, we have a constant acceleration, which means that velocity is going to be going up at a constant rate. But what does this mean for the position versus time graph? Well, the position versus time graph, if we look at our previous kinematics equations, the position versus time graph should be a parabola. That means that position is proportional to t squared, which it seems to be. While the slope in the line, the change in position over change in time, was given by velocity in the uniform motion example, the velocity is changing in this case. So what you need to do is look at the instantaneous slope, which is called the line tangent to the curve. It is a line that just barely touches the curve at any given point, like these three lines, and you'll see that the slope of these lines is going to be equal to the velocity at a given time. So it starts out with zero slope, it gains a higher slope, and then it gains an even higher slope as velocity is increasing. And this is the meaning of acceleration. Velocity increases, which means that the amount of position that is covered over time increases as time goes on. So far, nothing that we've done has actually been physics, is just math, is just calculus, actually. Calculus was developed by Newton in order to explain the motion that he saw, and it is imperative that we have some idea of how to use it, even if we don't want to call it calculus. So, moving on to the actual physics, Galileo found that every object, no matter how heavy, would accelerate at a rate of about 9.81 meters per second squared towards the Earth. In this class, we will round this to 10 meters per second squared to make calculations easier. With no initial velocity, the speed of an object in free fall is given by v equals gt. And with no initial velocity again, starting from rest, the distance an object will fall in its free fall is given by d equals 1/2 gt squared. These are just the kinematics equations that we went over earlier, with acceleration replaced by the constant g, which is given by 10 meters per second squared. The way that he proved this was just to drop a heavy item and a light item from the Leaning Tower of Pisa and see that they both landed at the same time, despite what Aristotle would have you believe. Before we go on to an example of this in action, I'm going to go over some sign conventions for linear motion. Since linear motion is in one dimension, you are going to be going forwards or backwards in a straight line. So instead of having our vectors be pointing in any direction, they either go forwards or backwards. So from the origin, designate one direction to be positive and one direction to be negative. A negative velocity means that the object is moving towards the negative direction, while a positive velocity means the opposite. This does not mean that the object has a positive or negative position. For example, if you choose to describe a freeway as a one-dimensional system with north pointing in the positive direction and south pointing in the negative direction, then you could be south of your origin point of what you chose to be 0 and going north, which would mean that you had a positive velocity but a negative position. A negative acceleration similarly means that the velocity is becoming more negative, but does not necessarily say anything about the positive or negative signs of velocity or position. Looking at these position versus time graphs for a bouncing ball, a ball that is in free fall, we can see what we expected to see from the position versus time graphs earlier. That is that the position graph is a parabola and the velocity graph is a line with a negative slope, which means that it is starting out positive and getting more negative as time goes on because acceleration is in the negative direction. In this graph, you will notice that up until about 0.22 seconds, the velocity is positive, then it hits zero, then it becomes negative as it is accelerated downward. We expect it to become negative as it's accelerated downward, and we expect it to be a straight line because there is a constant acceleration. This proves that there is a constant negative acceleration acting on the ball. And the line of best fit that is given by this data gives us an acceleration or a rate of change for velocity of negative 9.776 meters per second squared, which is pretty close to the value of 9.8 meters per second squared, which we are expecting. Looking at the position versus time graph versus the velocity versus time graph, it starts out with the position versus time graph starts out with a steep slope and gets shallower and shallower while still increasing as long as velocity is positive. So velocity is decreasing, but it's still positive. Therefore, the position versus time graph is still going up. Once you hit that zero, though, it starts going down, and as the velocity versus time graph becomes more negative, the slope of the position versus time graph also becomes more negative and it becomes steeper. At the point in the middle where velocity versus time is equal to zero, the position versus time graph is at its peak. Because it is turning around here, it has a slope of zero, which corresponds to the velocity versus time graph. Doing a last bit of math before moving on, how long does it take for an object to fall a certain distance in free fall? The answer can be found with algebra by looking at our equation distance equals 1/2 gt squared, dividing by 1/2 g on both sides to find t squared equals 2d over g, and then recognizing that taking the square root of t squared is going to give us plus or minus t, where the square root of t squared is equal to the square root of 2d over g, which gives us t equals plus or minus 2d square root of 2d over g. So because time generally moves forward, we're going to choose our plus value because we started at a time equals zero and we want to see how long it takes to fall down, not how long it would take if you were moving backwards in time. In overview, we have these three vector quantities: position, which is San Francisco or Livermore on the map; velocity, which is speed and direction, given by San Francisco, plane leaving San Francisco at a velocity of 300 kilometers per hour moving east. And acceleration is the rate of change in velocity due to a change in speed and or direction. So if you have a change in speed but not direction, that is going to be something that is like pumping your brakes or accelerating on the freeway where you do not change direction, but you do change speed and therefore you are undergoing an acceleration. A change in direction but not speed is given by this graphic where a car is going in circles at 40 kilometers per hour, but since it is going in circles and changing direction, it is undergoing an acceleration, which is going to be important once we get to circular motion in later chapters. And then you can also have a change in speed and direction. Thank you for your time. If this didn't already make sense, I hope it does now.